Hello everybody, my name is Oz Sunai. I'm the Vice President of Research and Development at Open Networking Foundation. In this capacity, I oversee all mobile-related projects. I would like to thank the organizing committee for their invitation to take part in this year's event. I'm very excited to present to you Aether, ONF's Enterprise 5G LTE-Edge-Cloud-as-a-Service platform. In less than a year, we have advanced on Aether rapidly, all the way from innovation and architectural design to rounding up the ecosystem, development, and operationalization. I will also give you an overview of our latest mobile-related project, SD-RAN. This project is evolving at a very rapid pace as well. As you know, ONF is a non-profit operator-led consortium driving transformation of the network infrastructure and carrier business models. Since its inception, ONF has built solutions by leveraging network disaggregation, white box economics, open source software, and software-defined standards to revolutionize the carrier industry. We have been successful on a number of fronts. We have started with the packet switching industry by delivering ONOS, our SDN controller, and associated control applications we call Trellis, as well as Operflow specifications. We have then led the evolution of this architecture by bringing full forwarding pipeline programmability with P4 and P4 runtime. We have successfully disaggregated and SDNized broadband networks with SIBA. We have also done the same for the optical transport networks with ODTN. Currently, one of the main focus points at ONF is to contribute to the disaggregation and SDNization journey the mobile networks are going through. Let me quickly go over what I mean by disaggregation, virtualization, SDN, and distributed cloud in this context. Consider this high-level illustration of a mobile network. We have the radio access network connecting the end devices to base stations or small cells over the mobile link using a specific spectrum band. We have the mobile core network that serves two purposes. It forwards traffic back and forth between the RAN and the egress of the network, from which we reach the applications we want to consume, and also while doing that, controlling the traffic, specifically conducting mobility management control, session control, subscriber control, policy and charging control, lawful intercept control, etc. Disaggregation of the mobile network starts from the mobile core. The first step is the disaggregation into control and user planes. Next, we can conduct further disaggregation by splitting the mobile core control plane into its functional components. Similarly, we can disaggregate the RAN as well. Following the ORAN architecture, this disaggregation may split the RAN protocol stack into components so that we have the radio unit at the antenna sites, the distributed unit at the cell site, and the user plane control plane separated central unit running from a data center and pooling multiple DUs and RUs. And once disaggregated, we can then softwareize these network functions so that the VNFs can run on commodity hardware. Okay, we can then make use of a data center that leverages an SDN infrastructure to run these VNFs. This infrastructure could be based on the next generation SDN principles, where the programmable forwarding elements run Stratum OS on them, and a centralized SDN controller could push P4 programs to establish the pipelines and subsequently use P4 runtime to control these pipelines. And the role of SDN does not end here in our context. Realizing that the small cells and the base stations are nothing but specialized forwarders, we can apply SDN principles to turn them into programmable entities as well. Then, the radio resource management components in the RAN protocol stack could be centralized to run as SDN applications on a RAN-specific controller. We could also consider developing P4 programs to run the RAN CU and the mobile core user plane functions for gains on performance as well as security. So we have disaggregated, virtualized network functions for mobile connectivity and software-defined control of the access network. Now they can all run from data centers. The next step is to architect the overall network towards an optimized operation for a given use case or use cases. This means deciding where to run which component and transform some of these components so that they can start pooling others that are running in a more distributed manner. Specifically, some of these network functions will need to run at cloud locations that are at the edge. The reasons could be because they require low latency or traffic localization, or that the transport network costs need to be kept reasonable. In our case, the goal to architect a system so that connectivity and edge cloud management may be offered as managed services to the enterprise, while empowering it with the capability to programmatically localize some of their traffic, manage their subscribers, policies, etc., is essential. So Aether is a distributed multi-cloud architecture that enables exactly this. So let us then set the stage. Consider the following premise. We have an enterprise with employees and visitors. The enterprise has a production line and engineers that oversee it. There are meeting rooms that consume multimedia. And there is an on-prem data center. Even though more and more of the workloads are pushed to the hyperscalers, there are still some workloads and databases that are local. There is surveillance for security reasons. But most importantly, imagine that this enterprise is transforming itself towards Industry 4.0. So as such, it is transforming its processes, manufacturing, and machinery towards automation. And to enable that, it is deploying more and more sensors, cameras, IoT devices on its premises. So to this environment, Aether brings two distinct components. An Aether connected edge, which is effectively a micro data center leveraging an SDN infrastructure and running Kubernetes. Aether Connected Edge is constructed using commodity white box components. And the second is the suite of small cells to provide coverage and capacity for the private network. Now, depending on the use case, these small cells may be operating an operator's license band spectrum, or CBRS in the States, or an enterprise's own license spectrum for private use in other countries. Included in Aether is also ONF's open source mobile core, OMEC, that is distributed between the edge and the public cloud. OMEC has been architected to allow its control plane, we call this the Aether connectivity platform, to oversee multiple user planes, each one running on a distinct Aether connected edge at a potentially different location. The presence of the mobile core user plane at the edge allows for a local breakout, which in turn empowers the enterprise to programmatically keep some of its traffic local. Since Aether includes its own mobile core, it also provides the enterprise SIM cards to enable private network connectivity. Aether also has an Aether management platform that conducts operational control and central monitoring of all Aether connected edges. The platform also conducts lifecycle management for these edge locations. Aether disaggregates the network and edge cloud control between the service provider, whoever it may be, and the enterprise. Specifically, the enterprise is empowered with controlling its own traffic, deciding which flows stay local, which flows go out, who accesses which services, and which applications may run all or some of their components on the Aether edge. Then, on the enterprise premises, we have small cells and an Aether edge. The Aether edge hosts mobile core user plane workload, which is controlled centrally from the public cloud, giving us connectivity as a service. Aether also enables connectivity to all public clouds. Further, the edge components of the machine learning and artificial intelligence platforms that are available on public clouds run on Aether today. This means that the edge components of applications that leverage these platforms and their APIs can natively run on Aether. Aether can also run any other enterprise edge application that can run on Docker containers. Through a central platform, Aether enables enterprise edge management and control. And a work in progress, Aether will soon enable network slicing with slicing policies, slice traffic flow rules, and per slice subscriber mapping, all controlled by the enterprise through a portal. Now, let us look at Aether's building blocks. At every edge site, we start with an SDN fabric that allows for a programmable forwarding pipeline. For this, we use Tofino-based P4 switches that run ONFs SwitchOS Stratum on them. Stratum allows the switch to be controlled, configured, and managed using P4 runtime, GNMI, and GNOI respectively. This fabric is controlled by ONF's SDN controller, ONOS. Running on each switch is the fabric.p4 program that describes how we want the fabric to process these packets. The corresponding fabric control application running on ONOS allows us to control the fabric according to this description using P4 runtime. Running on these switches is the in-band network telemetry framework, or the INT, that allows the collection and reporting of network state by the data plane without requiring intervention or work by the control plane. This is an important piece since it enables us to collect fine-grained measurements from the fabric, which will then be used for network verification and closed-loop control. All of this is happening at each edge site. The software components, ONOS, the applications, the telemetry collection platform, and the verification platform are all containerized. And they need compute and memory resources for a scalable and elastic operation. This means we need servers and a container management platform. This is Kubernetes for us. And our edges are 4G, 5G connected. This means we need small cells connected to this fabric. Now, mobile connectivity, as you all know, requires the mobile core network and the user plane and control plane separated OMEC is the core network for Aether. So in our context, we realize the user plane, that the local breakout, using the P4 paradigm, so we can bring programmability and INT to the mobile network as well. So this is done with an extension on the fabric.p4 program running on the switches and a corresponding ONOS application that not only controls the user plane using P4 runtime, but it also interfaces with the mobile core control plane for 4G and 5G specific control operations. The corresponding mobile core control plane runs from the central cloud, and in the Aether context, we call this the Aether connectivity platform. So this could be a hyperscaler cloud or a central cloud, a telco cloud, a private enterprise cloud, etc. And we also SDNize the 4G, 5G RAN. So this effectively means disaggregating the RAN and then further disaggregating most of the radio resource management functions that control the mobile link from those disaggregated components and realize them as SDN applications running on an a RAN optimized SDN controller that we are developing using ONFs as the baseline. So with this, we have an operational Ether connected edge, but we would like to have many edges in the network. So when you have many distributed edges, a centralized management platform becomes necessary to operate this network. For this purpose, we have the Ether management platform. Ether has been operational since December of last year. The first ACE has been at ONF's Menlo Park office with the connectivity platform and the management platform running in a highly available manner from Google Cloud's US West server farm. We rapidly expanded the network with more ACEs around the globe. We now have one at Intel Labs in Hillsboro, one at ONF's Tucson office, one in AT&T's 5G lab in Atlanta, one at an NTT office in Osaka, Japan, and also two European locations, one in Telefonica in Madrid, and one in Türk Telekom in Istanbul, Turkey. The last addition has been Ciena's 5G lab in Montreal, Canada. All of these sites, the SDN fabric is Operflow based. And starting with our Menlo Park Ether connected edge, we are indeed now bringing P4 programmability to Ether. One important thing to mention is that Ether is effectively an operational network. So we also need to get our hands dirty with all aspects of operationalizing a distributed cloud-based mobile network. We have been focusing on two aspects of this so far. First is automating the new edge and new edge application deployment and lifecycle management aspects of our network by stitching widely used platforms for our purpose. We're effectively trying to make our lives as the network operator easier here. Next, we have been focusing on developing a true CI/CD pipeline for the network. This is important as we are constantly upgrading our system, doing bug fixes, bringing new features at every level of the platform. For this purpose, in addition to our production edges around the world, we have development and staging edges. On the development edge, we work on new features and patches and conduct unit tests. Once these tests are passed, we migrate the workloads to our staging edges, which are effectively replicas of production edges. Here we do system-level tests, making sure our patch or new feature does not jeopardize network operations. Once we're convinced that this is not the case, we migrate the workload to the production network. We have successfully demonstrated the operation of a number of edge applications on Ether. The first application came from us, an open source CDN implementation. Next, we had an application from Microsoft Research. For this, we brought in the Azure IoT Edge platform to run on Ether. We then ran Microsoft Research's ML-driven object identification application on Ether. We also had an ML-based smart spaces application from Infosys that required GPU resources at the edge. And last but not least, we had an application from Google Cloud that leveraged their AI platform to conduct food traffic counting in real time. So this brings me to a few key takeaways. Ether is ONF's open enterprise 5G LTE Edge-Cloud-as-a-Service solution that seamlessly combines private mobile connectivity to an edge cloud and conducts combined orchestration. It is the first of its kind. Ether has a central edge cloud management and control platform overseeing all edges. It can run from any central cloud where one can run Kubernetes. Ether's mobile core control plane for connectivity runs from the public cloud, while its user plane runs at the edge. The control plane oversees many user planes, each hosted at a different enterprise location, enabling connectivity as a service. Ether is part of a multi-cloud solution for enterprises. As such, it enables connectivity to all central clouds. It has the capability of hosting third-party edge applications. And these applications may leverage hyperscaler platforms such as Google Cloud's AI or Azure's IoT Edge platforms. And Aether natively supports the APIs that these platforms present. Aether is ORAN architecture consistent. It already hosts a micro-ONFs-based near real-time RIC with plans to host DU and CU components in the future. The development of micro-ONFs RIC is part of the SD-RAN project. Our mission in this project is to enable true SDNization of the RAN in a performant, scalable, and highly available manner. This concludes my talk. Thank you for listening. Have a great day and enjoy the workshop.